Welcome everybody. Good morning, good afternoon, or good night, or whatever time zone you're in. Good evening. So this is the virtual seminar series that we have been doing for some time. Started in 2021. This is under the umbrella of IEEE Technical Committee on Cognitive Networks, and this is a special interest group in AI, and ML in security. So the chair of the group is Professor Subbalakshmi, and she is a fellow of National Academy of Inventors and is also a founding director of Stevens Institute for AI. And I am the vice chair. Unfortunately, Professor Subbalakshmi won't be able to join today's call, so I'll introduce our speaker. So to introduce the AI ML Security SIG group, we have currently 420 members in LinkedIn group, and we are constantly growing. To join the group, you can either go to this LinkedIn group link, or you can also search using IEEE AI and ML Security Special Interest Group in LinkedIn, and you'll be able to find it. If you cannot, feel free to send us an email, and either Suba or me we will respond immediately. So we started this monthly seminar series. We do take a break in summer, but we started this in 2020, and especially when COVID hit us and we were unable to travel, and we didn't have enough technical conversation, and that's how we started all of this. The first talk was given by Professor Vince Poor, and then we had, after that, 12 different talks by many prominent researchers in this field. All the recorded talks, or most of them, are available at the SIG website, which is over here, and is also available in our YouTube channel. So if we get permission from the speaker, then we record the talk and post it. For the logistics of the talk, everyone is muted on entry, and please stay muted throughout the talk. And also feel free to type questions for this speaker in the chat box, and we will and I will basically read this out at the end of the talk. So today's speaker is Dr. Timothy O'Shea. He's the CTO and the co-founder at DeepSig Incorporation, and also a research assistant professor at Virginia Tech. He's focused on building machine learning and AI native wireless baseband processing capabilities to enhance both the spectral and energy performance of future next generation networks, as well as leveraging AI-driven spectral and spatial channel awareness and sensing to optimize the multi-user and multi-access next generation wireless systems. He worked before being with DeepSig. He worked with wireless startups, Hawkeye, 360, and Federated Wireless in the seed stage. He also held engineering R&D positions with both US DoD as well as Cisco Systems. And he has authored over 50 peer-reviewed works and patents in the machine learning for communication space. He has been very much involved in IEEE ComSoc, IEEE Machine Learning for Communication, ETI, Next Generation Alliance, and Open RAN efforts to accelerate AI-driven communication systems and their adoptions with Next Generation RAN and Open vRAN. And today, he's going to talk about securing and optimizing wireless systems with AI-native and data-driven wireless signal processing in the physical layer. So from here, Tim, please take it on.
All right, thank you, Dula. Screen. All right. All right, though. So thanks for having me. As you said, I'm Tim O'Shea, so I'm kind of dual-hatted at DeepSig as well as Virginia Tech. And just a very brief overview. So DeepSig is a startup. We're based in Arlington, Virginia. and we're up to about 40 folks. But really, we were founded to look at building capabilities in this emerging area between machine learning, DSP, and rapid software productization. So we have folks from a lot of industry and academic backgrounds, but this is really our focus, is using machine learning to kind of help create future baseband capabilities. And I think, for myself, I worked in the kind of the cognitive radio space, I guess in the 2007 to 2010 time period, when that was a big thing. And then I think what happened is in 2012 and 2013, we started to see kind of deep learning really take off in computer vision and in natural language processing, and really change kind of the way you could build AI and machine learning systems. So I kind of wanted to start off talking about, what does AI native mean? Is this starting to be used more widely in the field? There's a lot of talk about AI native within the context of 6G R&D. And so what does it mean? So really, I think AI native is about letting AI and machine learning learn algorithms from data and from end objectives, rather than trying to build really rigid feature-based methods or rigid logic engines or expressions. And so this is really exciting, and we've seen this happen kind of first with AlexNet and a lot of the computer vision and object recognition networks, where you can now let machine learning tasks like image classification or object detection run from a large data set without really doing any feature design or writing any explicit rules or feature detectors. You can kind of learn this whole thing end to end. And in doing so, this is kind of an AI native approach, because it's learned kind of an end-to-end solution of a hierarchy of features and probabilistic rules based on the data set that achieve this end objective. So this is really a powerful thing that we couldn't do 10 years ago, because of the amount of data, the amount of compute required, the techniques, the optimizer techniques that we didn't have. But now this is kind of transforming many fields of signal processing. And some of the recent examples of this are like Google's Lyra 2 voice codec, which is getting, on the order of 10x compression improvements over many traditional vocoders. NVIDIA's work around video codecs for VTC type applications, which is similarly getting 10 or 100x improvements in throughput by using these kind of learned model-driven compressions. Similar results from Facebook AI research in music hypercompression, and then really some pretty incredible results recently around things like stable diffusion and ChatGPT that are really, really amazing with this kind of end-to-end data-driven learning can do. So, this has also been called software 2.0 in some contexts. I think this was termed by Andrej Karpathy at Tesla. And the idea is really that, rather than writing a lot of explicit logic and explicit thresholds for decision-making throughout your software, what if you can write the entire kind of processing algorithm for your task that you're trying to build, and make it such that all the parameters are kind of learnable, and that your whole program and your whole software is differentiable, so that you can now start to use all these sorts of differentiable or gradient-based optimizers to tune, all of the parameters in an end-to-end way throughout your entire application. And so this is really kind of an exciting new way to build software, because instead of trying to think of rules and handcrafted features and purely model-driven approaches to problem solving, we can really think about the end objectives and performance metrics and KPIs that we want our algorithms to achieve. We can use some rules and model-driven pieces of this as well, but we can also let it be heavily data-driven. And then the exciting thing here too is that this can also result in solutions that are dynamic, so we can adapt them to new data distributions, and efficient. So we can do this often with very efficient, low precision neural networks, and using a lot of efficient hardware like GPUs or neural processors or different accelerators for neural networks. So this transition, I think, is happening in many fields, and I think that DeepSig, we set up and dove down this pathway in about 2016 because this seems like a really inevitable transition for a lot of the signal processing that we do in wireless systems, to really follow these high-level trends that software and DSP are seeing. All right, so what are kind of the fundamental enablers, critical baseband processing tasks that define our wireless systems, right? And I think, from the focus that we've had in doing research here, we've kind of broken this down into two things. One is this real-time spectrum awareness, which has kind of always been a big piece of cognitive radio, is understanding what's going on in the spectrum. What does propagation and interference and spectrum sharing look like? How can we be aware? This is kind of that observe stage of the loop, right? What's going on in the world, what's going on around me, and then how should I react to it? And so this real-time spectrum awareness has a lot of important applications, both for security and for performance, in terms of understanding what's going on so that we can best optimize it, as well as understanding what's going on so that if there's security threats or incidents or malicious activity, we can react intelligently to it. And then the other big piece of this is accessing the spectrum. So given all the information we know about activity in the spectrum, about propagation, about any effects or interference that are going on over the wireless channel, how can we then best perform baseband processing to take advantage of it and to optimize for spectral efficiency, for energy efficiency, and for resilience to interference, and for kind of any of these end objectives in our wireless system. So I'll kind of talk through these two major classes of applications, that we've been working on and building on. So OmniSig is kind of our, what we've been working on in terms of software to do kind of AI native spectrum sensing and awareness. So trying to make sense very rapidly out of the spectrum around you, just kind of raw IQ data. And I think this is really exciting because, in cognitive radio, people have built sensing capabilities for many years, right, to do signal detection and to do decision making. But they've often had to be very, feature driven. So if there's a specific waveform that you're interoperating with, if there's a specific waveform that you're interoperating with, then you're often building a specific feature detector for that waveform. And it becomes very specialized, right, very quickly. And it can also be very compute intensive. And so the idea of having a kind of data-driven approach that can detect many different types of emissions through a similar approach without a lot of heavy feature engineering, and can do so very computationally efficiently, and be run at the edge, is something that's really critical to enabling this sort of sensing aware applications in wireless. And so by using some of the same fundamentals that work in computer vision, and kind of rebuilding them to work for wireless and high rate IQ data, we've been able to really create much more computationally efficient and also very general and very sensitive spectrum sensing capabilities that kind of provide this kind of conversion from high rate RF data into kind of nice metadata about what has been detected in the spectrum and where. So this is kind of the basis then, or I kind of see this as a foundation for then for spectrum sharing, for wireless intrusion and threat detection, or for interference and EMI type detection, or different spectrum sharing applications. This is really kind of a fundamental layer then to help enable our cognitive systems going forward. So if we start deploying these sorts of systems, one of the problems that's always been an issue in wireless security is you've had some solutions like there's commercial WIDS products out there today, but they're often very specific to one technology, right? You've got Wi-Fi and Bluetooth type WIDS systems, but then beyond that, you kind of have to go into this realm of SDR and based systems to look at broader spectrum applications. And often those look like, either just sending back IQ data or doing some sort of energy detection. And so what we wanted to do was take these kind of ML based spectrum activity recognition tasks and then put them right at the edge where the software radios have gigabits of IQ data, and then boil that down into kilobits of metadata that describes the activities and the actions that are going on. And this really starts to make it scalable, right? So now I can put tens or hundreds of all right. So right. So this makes it really scalable. Now we can have tens or hundreds of sensors that are combining metadata into a database, and it's a manageable data size. It's not terabits of IQ. And then we can start to use all kinds of algorithms on that metadata to do event detection, to do anomaly detection, and to kind of figure out what activities in the spectrum are most critical to. So these are just some examples of doing detection and classification within the spectrum. These are some examples of essentially using an RF object detector to localize interference that's behind a cellular carrier, locate specific types of emitters in very congested RF environments, and then also, in this case, locating and recognizing UAS type emitters. And so, there's been a ton of work in the literature around object detection and computer vision. And a lot of those techniques, they don't work perfectly in radio. We don't have images really. We have complex value data that has a lot of different effects going on. But we can really heavily adapt these object detectors for IQ data and for radio data, which is kind of one of the things we've spent a lot of time doing. And then use this to really do this rapid detection and classification of these events by optimizing kind of F1 performance metrics. And this is typically a supervised learning task, where you're using a lot of real data and labeled data in order to, train a network that can do this very efficiently. And this is nice because, there's a lot of optimized inference hardware for this. And so you can now do this very efficiently and kind of do these detections in low millisecond, or in some cases, microsecond timescales. So this is an example where you're in the ISM band and you're doing this kind of microsecond level burst detection and localization, where you're kind of using a machine learning based object detector and regressor to basically detect and localize every burst within this very busy, congested multi-user band. So it's really exciting that we can do this now. Like, these capabilities are available. This is really what this kind of machine data-driven ML within the sensor has enabled. So this is just an example. I think this data is no different from what you just saw, but there's been a lot of interest recently within how do you visualize these things in mixed reality? And I think for a lot of folks that don't work heavily within radio and the comms field, they don't have a great intuition for the meaning of that data, of those detections and those localizations. So this is kind of an example where we're putting these RF detections and classifications and localizations kind of onto an augmented reality view in real time. And you can really start to see then, how can we have such a, an instantaneous view of kind of the spectrum world around us. And so I think this is kind of a nice way to look at it, and potentially a really useful diagnostic tool for, for network engineers and for fault diagnosis in wireless networks. So what does this look like? So this is an example where you have now your kind of edge detectors running, and these are generating then these kind of raw record fields. So there's a format called signal metadata format, so SIG-MF, which is kind of an open source spec that the Green Radio project has helped to build. And so now you have basically an example of metadata that's been produced by a whole bunch of different edge detectors that are running. And so what we're doing then is we're able to take, gigabits of data. We've boiled that down into these kilobits of detection metadata. And now we're going to start to build these kind of density features that kind of describe the density or the frequency of different events within a feature space based on that metadata. So this is kind of like how often signals are occurring in different areas of the band, what their properties are, what their classes and types are. And so out of this, you now have a really concise way to build and track like pattern of life, and detect anomalous events and changes. So right, so we're creating these kind of density features. This is kind of an example of a three-dimensional density feature that looks at your center band, your bandwidth, and your RSSI, essentially. So you can start to get these kind of these densities, and then you can pull out kind of where is there anomalous behavior over a long period of time. And this is awesome because we can now archive the whole spectral pattern of life for facilities for months or years at a time, because the data level is really manageable, right? It's compact and it fits nicely in databases. So these are just some examples of what is an RF anomaly, and I think that there's a lot of different things an RF anomaly could be. So for example, here this is looking at in the 450 megahertz band, where there's different GMR radios. One anomaly might be, one channel is very vacant, and then suddenly you start having new P25 or DMR emitters coming online on a new channel that's never been occupied before. That's pretty anomalous, right? Similarly here, you have new emitters coming online. This is another one where you have kind of a stable band of operation in the 855 megahertz GMR band, where you have stable emitters typically, and then suddenly you start seeing a signal hopping across the band that's not typically there, and it's kind of creating these new modes in the density distribution. So this is again an anomaly and a change that you might want to look at. It might be of interest. Similarly, in the drop, so in the 880 megahertz drop, this is a case where you have multiple cellular carriers that are represented by these modes in the distribution. And essentially, if you suddenly have one of them dropped, or power level changes, or carrier goes away, then this is indicative of something like a cell tower failure, or possible interference in the band. And so this again is an anomaly. It's a change that you might want to call attention to. So it's really, how do you take all of this super high rate IQ data and then boil it down more and more into like metadata of all the events, and then metadata of the interesting events and changes, and really start to make like an actionable event, that you can work with typical CMs and fusion with other sorts of data, looking at the whole spectrum. So this is one of the methods that we had looked at recently, then for doing this kind of metadata-based detection. And this is some work jointly with Virginia Tech, primarily from Gopi Krishna. And you can find the link here for the work. But this was presented just a few weeks ago at the International Conference for Data Mining. And so this is really looking at, if we have those features now, what is the best way to really identify anomalous events? And so, we looked at a bunch of different methods, and this kind of contrastive adversarial anomaly detection was really one of the leading methods that we came out with that worked really well. And the idea here is that you have a GAN that has this generator and discriminator, where you're trying to decide, is this record or this density anomalous or not? And then you also have some amount of augmentation on the side, which helps to create kind of synthetic anomalies with some specific distribution. And then besides that, you have basically this supervised contrastive loss, which tries to help kind of in this latent space that's kind of halfway through to the discriminator. It's trying to sort of apply these nice between class and within class penalties for how concentrated and how separated the anomalous and non-anomalous events are from the synthetic anomalies. And so this is a kind of a supervised contrastive loss. So using these together is really effective in helping to pull apart these anomalies and through this sort of a method. So looking at this, we compare to all of the traditional methods. There's tools like isolation forests and single class SVMs that are widely used in anomaly detection to do kind of this out of distribution detection. But then there's also been these methods recently proposed looking at like fanoGAN and UNet GANs, which are kind of more of a machine learning and a data-driven way to do this out of distribution detection. But this method works really well. So if you look at the CAAD method we just described, this is able to get significantly higher kind of F1 scores when looking at reliably doing anomaly detection on this kind of class of data. So this is kind of exciting to be able to get, very reliable anomaly detection over really a broad range of types of anomalies and different radio bands. So I think the security implications of this then are really powerful, right? Because we can monitor and identify anomalies across many different types of spectrum when pattern of life changes. So on top of this, this was kind of another method we introduced, which is looking at bringing in expert feedback. And so the idea here is that, you don't want a human to have to label, millions or billions of examples, but if you structure this task in a way that kind of the most uncertain instances can be pushed to a human for kind of curation and for supervision, and then you kind of allow a human to provide feedback and labeling in just those most uncertain examples of anomalous behavior. This goes a really long way towards improving kind of the ability of the system with kind of minimal human supervision. So this is kind of what you would really want for deploying this in production, have some kind of light monitoring and supervision that leads to better event detection and threat detection. So this is just kind of an ablation study then looking at that, where you can see that, as you add each of these effects, so right, so as you add the expert feedback, as you add uncertainty quantification, and as you add the contrastive learning, and then as you look at two different network architectures, you can see each of these contribute to kind of the F1 score ultimately of this resulting system. So all of these kind of compound to give you a really powerful technique for this sort of RF anomaly detection. So this is also interesting to visualize. So you can look at this in the latent space. So this is that latent distribution of anomalies and non-anomalies kind of halfway through the discriminator. And you can see here that, just by a little bit of that expert feedback, where you have these true and false anomalies here, you've really helped to separate them by just supervising kind of a few of the examples in this border region. And so you can kind of see the latent distributions of these separating out, which is pretty cool to visualize and see that working. All right, so then switching modes, from sensing, because I think that's hopefully now providing a lot of raw data for helping understand what's going on in the spectrum around us, and helping use it to secure and optimize our spectrum sharing and spectrum access, to the side of how do we actually use machine learning then in the baseband processor to do better job of the modem itself and the layer one for transmission and reception of data. And really what our focus has been on, improving wireless experience, which typically means improving spectral efficiency, improving coverage, improving sensitivity. This is really, the big focus of how do we push more through the spectrum we have, and reducing operating costs. So if we can use models that use less compute and less power and less cores than kind of the traditional algorithms that are used today, then this translates directly into kind of savings and more efficient wireless systems in the future. So these are really the two main motivations then behind why does it make sense to do this kind of AI native approach within the modem and the physical layer. So I think that if I step back first, there's kind of an evolution now of AI native signal processing into the RAN. And so, we're not going to just overnight jump to everything in the modem, from end to end is designed with machine learning. We're kind of having this incremental step towards that. And I think that, initially we're looking at, and a lot of the use cases are very well controlled kind of segments of the modem. And these are kind of transparent drop-ins into existing modems. And so this is kind of mostly an implementation, where are the key algorithms within these systems that help to define the performance of these systems, where we can put in kind of approximate machine learning algorithms that are lower complexity and give us better spectral efficiency. And so this is really the first and most immediate place for this that I'll go into in more detail. And then we're starting to see, within 3GPP release 18, this 5G advanced discussion of study group around using machine learning for some limited tasks within the spec, which would actually need to be standardized and interoperable between different vendors. So this includes things like, how do we use machine learned embeddings for channel state feedback that are more accurate and more compact than kind of some of the code books used today, in order to reduce network overhead and improve kind of performance in those conditions. And there's also been some discussion of potentially starting to standardize receivers, with kind of this neural receiver approach, in order to help, improve the general performance that the standard guarantees, rather than just leaving that to implementation. And then finally, there's been a lot of work recently around, what technology will go into 6G. I know the NextG Alliance here in the US is very active in this area, and there's many other groups around the world looking at 6G technology topics. And I think this AI native air interface is a really exciting one, because this is looking at, if we let the modulation and the framing and the pilot design and all of these kind of layer one functions within the modem, then can we really do better than we can today with our typical kind of OFDM, QAM, LDPC type systems. So this is where things start to then be, much more end to end, rather than some of these which are kind of a component within an existing end to end system. So I'll kind of glaze over on this, but I think that one thing that's happening as well is that, Open RAN and vRAN are both kind of growing, and the will to try to, commoditize and virtualize a lot of the baseband processing equipment is really growing, to try to make deployment of these different RAN systems cheaper and more efficient. And so this is kind of nicely timed at the same time that these technologies are maturing, because using these neural processing methods is a really nice way to get much better cost and power efficiencies in these systems, and allows them to adapt, be more adaptable than many prior methods, and allows us to use the spectrum awareness to really try to help optimize spectrum consumption and sharing and scheduling and allocation. So what does this look like for us? We've been very focused on the layer 1, and this is the hi-fi typically. And so this would be looking within the baseband unit or the VDU. And I think that this is, where a lot of things are headed, is that you're going to have these very low latency, efficient inference algorithms that run within the radio unit and within the DU to do this high rate signal processing that really defines the performance and the KPIs of the air interface. And meanwhile, we're starting to see things like this radio intelligent controller that exists in the cloud or in the operator network as more of a commodity server that can probably do the tuning and the training and the model updates and the model management for these kind of edge inference algorithms. So this is kind of the model that we've been working with, is that, as we build these kind of inference algorithms like the neural receivers to push into the DU, the RIC can then continually monitor their performance, fine tune their performance for the locale that they're deployed in and the effects they're seeing in the channel, and kind of continually monitor and improve them. So I think that this data-driven way of doing PHY design is really nicely aligned with where Open RAN and vRAN are headed. So then this is an example. I think it was about a year ago, we completed our first kind of AI native 5G call on top of an Open RAN system. And so this is basically using a commercial UE with a 5G Open RAN network, where all of the push uplink receiver processing is being done by a neural network that's able to kind of do all that symbol estimation and recovery in a neural way, which gives you significant throughput, load and latency benefits, and can really help improve link margin and spectral efficiency. So this is just kind of an example running in our lab of a side-by-side comparison of the neural receiver and the traditional kind of linear MMSE receiver. And you can see kind of benefits in both link margin and compute efficiency here. And in this case, this is kind of that transparent case where the neural network is performing a fairly limited task, right? It's taking a resource grid that's come across the open front haul, so unequalized OFDM symbols, and then it's basically doing all of the pilot estimation, the channel interpolation, and then the equalization and log likelihood soft bit demapping as an approximate learned algorithm, which can really provide major benefits over kind of the textbook linear separated scheme. Right, so this is kind of one of the big areas that we've been focused on. Then is by dropping modified L1 software into open DUs or into other components, you can really take advantage of silicon that's been optimized for neural network inference. For instance, Intel's deep learning boost and VNNI instructions are something that we've used heavily. And you can also allow for prioritization between computational and link margin and spectral efficiency. So one of the nice things here is kind of depending on the size of this inference network, you can trade off, between a very small network, which is extremely fast and low compute load, or a slightly larger model, which might, take a little bit higher load on the processor, but then gives you more spectral efficiency and more link margin. And so this kind of adds a whole new variable into tuning within the RAN, right? Because we can now deploy a whole range of different sizes of networks and solutions, depending on kind of the requirements and the top level optimization goals of the network and an operator. So this also continues in massive MIMO. So one of the biggest, areas where, data-driven and AI native algorithms are important are where you have model deficit. And this is certainly the case in wireless channel modeling, where we often have a very naive distribution, like a Rayleigh or a Ricean fading model, or we may have a TDL or a CDL type channel model, and we've kind of optimized all the algorithms in our channel estimation and in our beamforming systems and in our scheduler systems with these assumptions in mind. And so by letting this learn from data now, we're able to start taking advantage of all of the probability distributions that are in this actual wireless channel. So like the spatial distribution of UEs within the sector, the spatial distributions of reflectors and delay spreads and Doppler distributions. All of these are actually really nicely structured distributions because of the geometry and the layout of the sector. And so, if we can basically make all of these components data-driven, there's significant benefit over kind of the flattened or whitened distribution that we've been assuming, so forth. And so this is kind of then the next steps is really looking at, replacing channel estimation here with kind of a data-driven one. We have some results we'll be sharing soon about both of these pieces. And especially with beamforming, I mean, this really defines then the ultimate SINAR that all of your uplink and downlink user allocations or user streams are able to obtain. And so by using these kind of learned nonlinear beamforming methods, there's significant benefit in these systems. And really, as the number of dimensions scales in your MIMO systems and in your multi-user MIMO systems, using a data-driven method kind of has more and more benefits because there's more and more model deficit when you kind of keep making the naive assumptions. And so this is a big kind of pain point, I think, within 5G today is the cost and the power consumption and the tuning required for massive MIMO. And so the hope is that really with this sort of approach, this can really be significantly helped and automated. So stepping forward then again to, what if it were completely end-to-end, rather than just fitting into 5G today, what if you could design the entire kind of waveform start to finish as an AI native task? This is something we looked at the very beginning and kind of have been continually looking at. And so this is a case where you have, basically one neural network, which is taking your symbol or your messages, encoding them to be transmitted over a channel. You have some series of channel effects, which may be fading or interference or distortion, compression, noise, different receiver impairments, or different adversarial effects like jamming. And then ultimately you have a decoder neural network, which is trying to recover your transmitted messages S. And so this is kind of like a concise way to try to define the entire kind of joint optimization of a comm system, just as these these two neural networks and kind of jointly optimize them for any sort of channel impairments or structure that you want. And so in this case, we're showing, this is kind of the during training example of a very highly compressed system. This was a KU band PA model that was in high compression. And you can see that it converges to this really strange looking transmit constellation. But these are way out because they get compressed way back in. But it's optimized such that you have a very nice kind of cluster separation at the receiver once it finishes training. So this is just kind of an example of how can you use this end-to-end training to come up with a very nice solution with some difficult and kind of non-standard channel effects in the loop. And I think then there's many ways to extend this, and I think there's been a lot of interesting works that have been done since this. I think there's now this notion of the AI native air interface being considered for 6G, and I think this very much kind of mirrors this channel autoencoder concept, where you're looking at kind of the reconstruction loss of messages of some sort, whether that's bits or code words or content. I think once you start considering content, things like images where you have a reconstruction loss that might be something like a PSNR or similar kind of psychoacoustic distance measures for audio. Once you start considering that content level as well, then this term kind of semantic communications has been used, where you're really trying to kind of jointly optimize both the source coding and the content coding, for actually the content distribution and for the channel impairment distribution. And so this is really powerful, and there's been some really cool works showing that this has significant gain, even for things like for video codecs running over a fading channel, where we can do a lot better by learning a joint encoder than using kind of the conventional LDPC on top of a conventional like JPEG or MPEG type encoding. So this is kind of exciting to see this area accelerating. Then this is a little bit more work from on what we've done in this area. So had this IEEE Spectrum article 2 years ago that kind of documented some of our early work working with NASA to do these kind of end-to-end learned channel autoencoders running over the air over the TDRS satellite system. And now this is kind of more recent work where, rather than kind of learning single carrier channel autoencoder schemes, we're starting to learn kind of OFDM based autoencoders or autoencoders on other different basis functions like wavelet basis. You can kind of do this on a lot of different transforms or basis functions depending on kind of the objectives of the communication system. But one of the nice things here is this system here is trained with essentially a jammer, so like a kind of an adversarial jammer in the loop within that channel model, and it's trying to learn basically a big multi-carrier slot system to effectively reconstruct data over that slot. So it's including then an arbitrary mask and slot kind of resource allocation, but it's also coping with kind of a TDL channel model, as well as the presence of a very high-powered jammer in band. This is like 40 dB up versus all the other data. And in this case, this has been able to learn a solution here that still works really well. This is still able to attain like 10 to the minus third Burr before any sort of error correction is applied afterwards. And so I think from a security and a resiliency standpoint, this kind of learning encodings across wide time and frequency dimension encodings is pretty exciting for kind of this resiliency and interoperation in congested bands. There's a lot of interesting questions about how do you train these. So you can easily train these offline in simulation. As you start to deploy them and want to look at online training or distributed training. There's been a lot of interesting work in federated learning and ways to deploy and scale that. But I think there's a lot of really, active research areas around this that are far beyond what we've had the time to look at. But I think certainly some of the work around this deep joint source and channel coding, which is, ties directly into the semantic communications area. There's been a lot of really interesting work recently also around using this kind of reconstruction loss to do new FEC code design and new methods for FEC decoding that are kind of reduced complexity. This is what you're seeing here is a pilot free slot. And so it's able to kind of learn methods that embed a lot of that reference pilot encoding into the way the constellation is designed, so that you can really reduce pilot overhead in some of these systems. And there's been a lot of really interesting work also around, how do you use these techniques a little bit higher up the stack at multi-axis schemes. So, if we let ML kind of make some of the decisions about access times and multi-axis, this can be a big help. Similarly, for looking at kind of neural MIMO and spatial processing, I think that there's some really interesting works looking at, if we start to look at new encoding schemes and new ways to use degrees of freedom, from an end-to-end learn perspective, there might be, some very efficient solutions out there. And then lastly, energy efficiency is such a huge thing, especially as we look at wider band systems and millimeter wave or sub-terahertz bands, or even lower bands, going to just lower bit resolution and more nonlinear hardware that can be cheaper and operate at higher efficiency points is a really exciting area for, how do we make all these systems, cheaper and more resilient so that these algorithms and software can kind of compensate for all of these things. So these are kind of exciting extensions, I think. So then kind of where does this all come together? I think, we've been kind of playing with both sides of this in terms of the sensing and sense making in an area, as well as kind of the end-to-end optimization of a comm system and all of its pieces in the physical layer. And so ultimately, I think that, there's been this discussion of digital twins within 6G. I think really where this makes a lot of sense is that, you have a lot of data from UEs that are out there in terms of what channel state information looks like, what interference looks like, what propagation looks like. And you really can start aggregating this data at a large scale, and then using this in your data-driven models to help do better, basically multi-user scheduling and assignment and prediction of how you can best utilize the spectrum and improve the density of these kind of MIMO systems. And so I think that, this is an area where, we're starting to work on really how do you bring together sensing for kind of out of network situational awareness that can go into the scheduler, and then how do you bring together, in network CSI measurement for that in network. And both of these give you a lot of information that you can then leverage during scheduling and during kind of spectrum sharing and resource assignments. So that's kind of nearing the end here. I think really there's a lot of exciting research threads that are growing kind of towards where this is going in 6G. Ultimately, I think this kind of pervasive sensing and spectral awareness are continuing to grow, and they're becoming more practical. We can have this, on every G node B and every UE without a huge amount of compute or cost at this point. We have massive MIMO systems that are used widely today, and I think there's a lot of continuing to look at how do we combine this with distributed MIMO to do better, make use of kind of spatial control of how we do multi-user pairing and scheduling and beam control. And so I think there's a lot of improvements in spatial reuse that we're going to have to get better at to make use of kind of the valuable low and mid bands where we get great propagation and great properties. And then I think, yeah, within the AI native air interface, certainly we're seeing a lot of exciting potential within semantic communications for much improved throughputs for different types of applications. I think this optimization for things like low bit resolution and low cost non-perfect hardware compensation, and especially when you get up into some of the high bands in millimeter and sub-terahertz wave, where there's a lot of effects that need to be compensated for. These really offer one way to get there very efficiently. And then kind of cross stack optimization. So I think today we don't fully use all of the data we have in the CSI to help optimize L1 channel access. And similarly within kind of the L2 and the scheduling level, there's much more data to leverage there. And so ultimately I think that there's all this talk about the killer app and what will drive new verticals in 6G, but I think really from my perspective, I think that the whole RAN and comms community is turning a little bit more back to the fundamentals. So how do we make 6G like really cost efficient and make it work really well and autonomously without kind of expensive tuning and expensive power hungry equipment. And I think really driving that is going to be a major driver rather than just specific applications or use cases. I think it's really the ability of it to adapt and autonomously tune for many types of applications and get kind of better cost per bit essentially. So that's it. I'll kind of stop there and be happy to answer any questions or listen to feedback.
Sure. Thank you, Tim. That's a wonderful talk. So from audience, if you can post your questions in the chat, that would be really great. So before the audience kicks in, I have one question that I would like to ask you. So a lot of these work that you have been doing on signal detection, some of the work, is there any work which is mostly on low probability of intercept and low probability of detection signals? Because some of these signals often are hidden under the noise floor. So how do we use machine learning techniques to attack these problems?
Yeah, I think that's an interesting one. I think we've not been super focused on that specific problem. I think often when you think of like orchestration between networks, you're looking at kind of the above the noise emitters that are readily available, and especially in kind of most commercial applications, that's the focus. I think there has been some work showing that those similar techniques can be applied to much lower power LPI type signals. It's not something we've done a whole lot of work in, but I think that it really comes down to I think typically you need some amount of structure that you're relying on, right? And if you kind of can start assuming some amounts of structure in that LPI signal, then you can still very readily learn kind of those features using these same methods. I think obviously you need to probably start looking at larger observation windows, and if you need a lot more integration gain, just to get the kind of signal to noise ratio out of your features, then you certainly need the observation data to get there. But I think we're at the point where so many of our wireless systems, we're kind of like throwing the easy 80% away, where we should be aware of and acting on all this information. And then, those super low power signals are then kind of the increasingly difficult, piece that's hard to learn in the general case as much.
Sure, sure. So I don't see any questions from the audience. Maybe if anyone wants to ask a question, if you want, please go ahead and unmute yourself at this point and feel free to ask a question.
Yeah, I would love to.
Okay.
Like to ask a question.
Please go ahead.
Hi, Dr. Osha. I'm Shubham. Thanks for the great talk. I have actually two small questions. You mentioned that like skipping the system parameters while designing the ML models will make the model trivial, but how much we can incorporate these parameters while developing a machine learning model before the model complexity becomes unrealistically high?
Yeah, no, that's a great question. I think that machine learning has a super broad range of model complexities. We've seen some of these models like GPT-3 and GPT-4 that have billions of parameters and are extremely large models. I think, we've had a lot of focus looking at, how can you make the smallest model possible in terms of parameter count and MAC count for compute. And I think that there's a lot of techniques. So there's a paper called EfficientNet, which was one of the big early works in this area in computer vision. And there's just a lot of different architectural techniques in how you build the neural networks, which can drive down both the parameter count and the MAC count drastically. So I think there's a constant question when building these ML models in comms for, how small can you make it where it can still achieve good performance metrics. So we're kind of, we'll do a lot of hyper optimization where we explore, millions of different model architectures, and we can kind of draw an efficient frontier of complexity versus, communication system performance. And then I think you always have to kind of be cognizant of where that boundary is. There's been a handful of works that just use kind of a generic DNN of large sizes for a lot of applications. And I think that's usually not realistic because, often the complexity is much higher there. So I think a lot of thought really has to go into what are the right architectures, for doing this efficiently.
Okay, that makes sense. My second question is, in one of the slides, you have shown a side-by-side comparison where the one of the ML model and the linear MMSE receiver is equalizing the symbols, and we see the constellations. Could you specify which one was the MMSE receiver and which one was the ML model? I don't even know the slide number because it was not visible on this screen.
Yeah, I think that that one was just kind of a monitoring for the two of them. I think we have some quantitative results comparing those in the white paper we put out. I don't think in that image it's called out specifically.
Okay. Thank you. Those were my questions.
Thanks.
So is there anyone from the audience who would like to unmute and ask a question?
Sure, I have a question.
Yeah, please go ahead.
So from the white paper with Intel, it looks like that was heavily dependent on the 3GPP channel models, which have often been thought to be highly inaccurate from real-world channel models. if they are inaccurate, how would that affect real world performance over the air?
Yeah, definitely. Those results did rely on the 3GPP, TDL and CDL models. And I think that the learning process of taking that and going into over-the-air environments is something we're still improving at. I think there's been some work recently on making better models that have like spatial consistency and these sorts of things. I think one of the things that we've done is we'll take a model that's pre-trained on a 3GPP model and then deploy it over the air and then do some amount of fine tuning on it to try to leverage the real world distribution better. I think kind of what we've typically seen is that those models they're kind of more whitened, right, in a lot of aspects than the real world distribution, where you have kind of a lot of fixed kind of delays, reflectors, and fixed geometries. So yeah, I think that's still an area where there's a lot to be done in terms of improving the models. And I think there's a whole nother area of like ML driven channel modeling as well, that's continuing to develop, as well as non-ML based channel models. And I know there's also been some work in trying to do much more rich ray tracing based models for this too. I think we've seen reasonably good generalization from those to over the air, but I think that you're often going to extract more a better model fit by doing that fine tuning over the air. So that's ultimately kind of the method that we've been looking at for deployment.
All right, thank you.
To follow up on that question, do you see more lifelong learning showing up in this context, or we're still not there yet?
Yeah, I think right now we're starting to try to do some of our earlier trials here where we're taking these models and going out into a couple macro cells and continuing to look at the performance of them and how well they generalize, and then what fine tuning we can do to improve their performance. I think there's an interesting question of like, what if I have one of these in every of a million sectors in a network? How should I manage the training data, the models? Should I be just training a specific model for every sector? Should I be doing some sort of a shared learning or like clustering cells into different types or different distributions, modes? So there's still a lot of unanswered questions about like what's the right way to do this, managing this whole life cycle of learning. And it's not all super clear yet, but I think we've seen a lot of good performance just from tuning single cells over time. But I think we're going to have to get better at like finding rare modes and rare distributions and ensuring kind of resilience against those. We've kind of managed that today by doing a mixture of simulation with real data as kind of an augmentation to help keep generalized performance. But there's always a trade-off between model generalization and specialization.
Sure. And that also relates to the fact that at some point in time, we will have to move to a different model. Maybe when I'm inside a room, there's a different model than when I go outside, or when I'm in a train, the channel model should be different. And basically the transmitter constellation would look different because of the channel being different, right? So how do we detect those channel changes and adapt to it, basically? And how fast do we have to do that? That's I think is one of the questions that I have.
Yeah, definitely. Well, and because a related piece of that is, how quickly can you learn for a new channel or a new distribution, right? And if it's a super fast moving train, you may not have time to do much adaptation. So I think, in the simple case, which is like looking at a specific sector that sees kind of a distribution of propagation effects for the users in that sector, it's reasonably stable as a distribution. If we were to think, less about that neural receiver case and more about the end-to-end autoencoder case, where you might use different modulation schemes given different channel properties, there's still a lot of work to do. Like, do we need to start, clustering users into different channel modes and then kind of learning pre-learned schemes for each one, and then having some selection scheme? I mean, we do this with MCS today just based on, block error rates essentially. But you could think of that could become a much smarter problem where, the localization, the delay spread and Doppler statistics, the content type, all of these could go into the selection of some sort of different encoding that gets selected at either end of the link. But yeah, there's now a whole list of how do you do that optimally, right? What are the schemes that we should standardize in that sort of a system? And then, how do we do selection? There's certainly a lot of unanswered questions at this point.
Sure. So someone from the audience, if anyone wants to unmute themselves, ask a question, please feel free to do so. Okay, so I don't see any more questions from the audience, and the chat is also not showing up any more questions. So at this point in time, I would like to thank our speaker. Thank you, Tim, for accepting the invitation and talking about all the exciting work that you're doing. And I hope that I'll be able to post the video after the talk. And with that, I would like to thank the speaker.
All right, well, thank you for having me. Thank you all for attending. I know I had to compete with the Senate hearing on FTX's collapse today, so I'm glad this was more exciting for you.
Sure. Thank you. Have a good day.
Thank you. You too. Bye.